Okay, guys, so welcome back. Welcome back. I hope you enjoyed your little 45-minute break. Hope you guys were able to rest and recuperate. And welcome back to our lesson. Hopefully you guys can notice a slight change to the presentation style. Here at the back, we got our nice Astron Energy banner, right? So hopefully you guys can see it looks very pretty, right? Everything is Astron Energy themed, okay? There we go. Okay, guys. So now we are going to kick off where we left off. We finished with question 5. So now we can start off with question 6. Now, in case you did not realize it by now, question 6 in your final exam and in your June exam and in your prelims will always be your Doppler effect or your Doppler shift is what other people call it. So let's get started. So what does the scenario say? Let me just get out my little test paper here. So it says a stationary listener. Oh, that's a very important word, guys. A stationary listener records the frequency of the sound emitted by the siren of a police car. Okay. When the car is traveling at a constant velocity of 26 meters per second, approaches the listener, the frequency recorded is 615 hertz. So this is when the car is coming towards our observer or our listener. Okay. The car passes the listener at time t1, then moves away from the listener. The frequency now is 526 hertz. So in summary, the car, this police van, is traveling at 26 meters per second. When it approaches the listener, that is the measured frequency. The measured frequency is 615 hertz. When the car moves away from the listener, the new speed, or sorry, the new frequency is 526 hertz. Okay. Question 1. What does it say? It says, state the Doppler effect in words. So it is your definition, guys, and this is your definitions according to your exam guidelines. 6.2 says, use the given information to calculate the speed of sound in air. So we want to know, okay, what is the speed of sound? In many cases, they give us the speed of sound, but in this case, they don't. All right. And you can't just assume it's 340 meters per second. Remember, that's not constant. Right? In different parts of the world, you have different air pressures. Different air pressures result in different speeds of sound, in case you never knew that. Okay, so we need to now figure out the speed of sound. So if we read this thing carefully, when the car was traveling towards the observer, what did we know? Well, we know that the velocity of our listener was 0. The velocity of our source, which was our police car, was 26 meters per second. The observed frequency, FO, okay, so I hear some people can't hear me. I've switched off my mic and I've switched it back on. If you still cannot hear, try exiting and re-entering the chat. Okay, hopefully I've turned up my volume. Hopefully you can hear it better now, okay? Okay, so guys, if you can't hear, try and exit and re-enter again. Anyways, the observed frequency when this car was traveling towards me is 615 hertz, okay? 615 hertz. The frequency of my source, I do not know that. Now, when the car moves away from me, what do I know? Okay. Now, see, guys, before I even get to that, look what I'm doing. I am writing down what I know. Guys, in your exams, and when you're answering a big question like this, the best thing to do is always to write down what you have been given. Writing down what you have been given means that you are actually able to visualize what you need to do. I always say that. Just write it down and then you can see, okay, what equations can I use now? Okay. Remember, now the car moves away. So the velocity of our listener is also still 0 meters per second. The velocity of our source is still the same. Nothing has changed there. The recorded frequency or my observed frequency, however, becomes 526 hertz. And what do I still know now? I still do not know the frequency of my source. I still do not know that. Now, what this whole question wants us to understand, we want to figure out what is the value of my velocity. Okay. Again, guys, I see some people. If you can't hear, please put up your hand. Because from outside, it seems like we can hear. All right. Let's just check. Right. From outside, guys, everything does seem fine. So I'm not too sure what the issue is. But if you are struggling, just try and exit and re-enter again. Okay, you see. Okay. Okay, perfect, guys. Anyways, now here's the thing. Let's look at this. This is my information when we were going towards, and this was information when we were going away. Now, we want to know what the value of the speed of sound is in air. However, I still do not know what the frequency of my source is in both scenarios. So I have two unknowns over here. What should be ringing in your head when you have two unknowns? It is the um, um, uh, uh, when you have two unknowns, what should be going on in your head? Simultaneous equations, all right? So I do not know the frequency of our source. I do not know the frequency or the velocity of sound. I know the frequency of the listener and the source. The velocity of our listener is 0 meters per second. The velocity of our source in both situations is 26 meters per second. They said the speed was constant. I've been given the observed frequencies. I just need to figure out what V is. So guys, I have laid the foundation for you. It is now up to you to figure it out what the velocity of V is. So I'm going to give you 4 minutes. It's supposed to be 5 minutes, but I've laid the foundation. So I'm giving you 4 minutes to find out what V is. So guys, good luck. We are diving into answering questions by ourselves already. So please, guys, 4 minutes to answer these questions. Good luck starting now. Okay, guys. So I'm seeing a lot of answers that the speed of sound is 333.33 meters per second. So, guys, you are correct. Well done. Now, can someone please explain to me? Because looking at all the answers that you guys have presented, all of the answers were correct. So, what is this thing about people saying physics is so difficult? All right. I mean, is it really? I mean, you guys are getting all the questions correct. So, well done, guys. You see, physics is really not that difficult. Anyways, so you are correct, guys. So, let me show you for those of you who might not still understand how we got to the answer. For those of you who got to the answer, well done. So, like I said, I first figured out that I had to do simultaneous equations. All right, that's number one. So let's start over here. I'm going to first figure out, well, I'm first going to work with a scenario when the car was coming towards me. So I'm going to start here, towards. So what do I know? Well, I know that the observed frequency, or the frequency that we hear, or the FL, sometimes you guys call it that, is equal to V over, oh, sorry, yeah, V, that's the speed of sound, plus or minus the velocity of my listener, divided by V, plus or minus the velocity of the source, times the frequency of my source. Remember, if it's towards, it's plus on top, minus at the bottom. So it's a plus and a minus. Always remember that, guys. Now, here's the thing. I can just start substituting in my values. What was my observed frequency? It was 615 hertz, and that is equal to the velocity of sound. Remember, the velocity of my listener was stationary. Okay, that's what I figured out. That's what I figured out. Okay, divided by the velocity of sound minus 26 meters per second, because that was the velocity of my source, and that's equal to the frequency of my source. Okay. Now what I'm going to do, guys, I'm just going to solve everything, all right, doing basic algebra. So this becomes 615 times V minus 26 is equal to the frequency times the velocity of our source. So therefore, the frequency of our source is simply equal to, well, if I multiply this out into my brackets, I get that this is 615 times V minus, this becomes 15,990 divided by V. All right, remember V is the speed of sound, and that's the first equation. Okay, remember I'm doing simultaneous equations. Now, what I'm going to do is I'm going to change color, right? Because I'm working with a different scenario. I'm just going to make it like this. Now for when the car was traveling away. Again, the frequency I observe is equal to the velocity of sound, all right, plus or minus the velocity of my listener, divided by the velocity of sound plus or minus the velocity of my source, times the frequency of my source. Remember, if it's away, it is minus on top, plus at the bottom. Okay, guys? That's the only thing you actually have to remember for Doppler effect. So now I substitute in my values. That's 526 is equal to V divided by the velocity of sound, which is V, plus 26 multiplied by the frequency of my source. I'm going to make the frequency of my source the subject of the formula. So therefore, the frequency of my source is equal to 526 times V plus 26 all over V. Okay? So therefore, the frequency of my source is equal to, if I do this on my calculator, I get that this is 526 V plus, what's this? This is 13,676 over V. Okay, guys. And that is my second equation. That's equation number 2. Right. So now I do my simultaneous method. I get that therefore, Fs is equal to Fs. So this becomes 615 V minus 15,990 over V is equal to 526 times V plus 13,700, or sorry, 676 divided by V. Now let's look over here. I have V in the denominator on both sides, so they can cancel. Okay, this can cancel with that because they're both in the denominator. So I'm left with 615V minus 15,990 is equal to 526V plus 13,676. You do your basic algebra, all right? So becomes 89V, because I take all the V's to one side, is equal to 29,666. You type this all, you solve this on your calculator, and you get that the velocity of sound is 333.33 meters per second. And there we go. An easy 5 marks on the plate. You just had to figure out simultaneous equations. And I have Sarah asking, sir, how do you identify that you have to use simultaneous equation? Because I have a tendency to just do both frequencies as Fs and Fi. So someone answered, you have two unknowns in both. Thank you. So if you, that's why I always say, write down what you have been given, Sarah. If you write down what you have been given, you realize, I do not know the frequency of my source, and I do not know the velocity of sound. There are two unknowns. So what do I do with two unknowns? I have to use simultaneous equations. However, I will admit it does take a little bit of practice. So you actually have to practice some examples where you use simultaneous equations for all that, not just for Doppler, for all the stuff. And you see that I lost my train of thought now. Sorry. You see that the more you practice, the more easy it becomes to identify whether you have to use a simultaneous equation or not. So two things. Number one, if you have two unknowns, it usually means a simultaneous equation. Number two, you're going to have to do some more practice with different questions which require simultaneous equations, because then after time, you are able to identify it a little bit more easily. Okay, isn't the velocity of sound a constant? No, it is not. Like I said in the beginning, the speed of sound varies depending on the air pressure, depending on the type of medium, depending on the type of gas or solid or liquid that it's traveling through. So the speed of sound is not one of the constants. It does change. If I'm at a certain altitude, sound travels a little bit slower compared to if I'm at a lower altitude. Okay, so sound waves on Table Mountain on the very top travel slightly slower than the sound waves at sea level. Okay, so the speed of sound is not constant. Speed of light is a constant though in the vacuum. Anyways, so guys, hope that answered your question. Well done to those who got it right. Calculate the wavelength of the sound of the police siren. Okay, so we need to figure out what is the wavelength of the sound produced by the police siren. Well, here's the thing. I don't even know what the frequency of the sound is. But let's go back to my previous equation. I figured out how I can calculate it. All right. So I'll say that the frequency of my source or my police siren is equal to one of these equations. I could have used this one or this one. It doesn't matter. Okay. I'm gonna use this one. 615V minus 15,990 divided by V. And all I do is I substitute in the speed of sound. So that becomes 615 times 333.33 minus 15,990. All right, divided by 333.33. And therefore, the frequency of my source is 567.01 hertz. Have I finished the question? No. What is the question asking? I need to know what is the size of the waves produced by my sound. So I know that the frequency of the wave is equal to the velocity at which the wave travels divided by lambda, okay, or the wavelength. So therefore, the wavelength of my source is simply, if you rearrange this equation, it's simply the frequency of my source divided by the, oops, whoa. I now made an error here. So you guys, you must also be very careful when answering. You don't want to make silly mistakes. It's the velocity of my source divided by the frequency of my source, okay? That just comes from rearranging the equation. So this is equal to, what's the frequency of sound? That's the velocity. What's the velocity of sound, guys? It's 333.33 meters per second. What's the frequency of my source? That's 567.01, because I've just calculated that. You type this onto your calculator and you get that the wavelength of your source is 0.59 meters. And there we go. That makes sense. Okay, so you first had to figure out, okay, what is the frequency of the source? Using that information, you can calculate the wavelength of your source. Okay, guys? I hope you guys understand it. If you don't, you may feel more than free to ask in the chat. And again, guys, I did get a few messages now during the break. We will record these lessons and we will make these lessons available later today or later this week. Anyways, moving forward. So now it says, sketch the graph of the recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then away from the listener. Okay? Label time t1 on the graph. No values need to be indicated on the frequency axis. So remember, on my y-axis, that's the recorded frequency in hertz. On my x-axis, that's the time in seconds. And t1 is like somewhere over here. Now, what happened? Remember, the car approached my listener. We had a certain frequency. The car passed us. And what happened? We got a different frequency. So originally, we had a certain high frequency of, I know the question says you don't have to, but I'm just going to indicate it anyway. We had an original frequency of 615 hertz. That is when the car was coming towards us. The car passed us, and what is the new observed frequency? 526. And that all occurred at time t1. So your graph would look something like this. That, and then what you do is you go you make a little asymptote dot over here, and then after the car passed us, this was our new frequency that was recorded. Okay. Now that is your go-to graph. If a car approaches you, that's your original frequency. Then as the car passed us at time t1, the frequency decreased, and we have something that looks like this. Okay. Do we understand that? Okay. I hope we understand that, guys. All right. Perfect. If you understand, you can give a thumbs up. Perfect, guys. Thank you. All righty. So this wasn't not too bad. I think it was just that simultaneous equation that might have caught out a few people. All right. So now let's get to question 7. And I used to hate question 7 in high school because this was electrostatics. All right. And I know many people used to struggle with this. So what does it say? Let's go to question 7. It says X is a point that is 0.025 meters away from a 4 nanocoulomb charge. All right. They say, see the diagram below. So sorry, guys, I did forget to add it in. Here is our positive 4 nanocoulombs. And then here is point X. And they are about 0.025 meters apart from each other. So that's basically your diagram. Okay. Now, 7.1.1. Draw a net electric field, draw the electric field pattern due to the positive 4 nanocoulomb charge. So again, it's almost like your force diagram. You can draw a circle and then you draw your lines going out, almost like you're drawing a sun. Now, something like this, okay? Now, if you are dealing with a positive charge, I always think about it like this. If you are a positive person, you give off good energy, okay? So if you are a positive charge, your electric field goes off from you. It's going away from you. So therefore, your arrows go out like that. Okay. So this is the net electric field for our 4 nanocoulomb charge. Okay, you don't have to put it in there. I'm just explaining that. No, the number of arrows doesn't matter. It usually indicates the strength of your electric field, but they're not going to penalize you for putting 10 arrows, right? Just don't put 1 arrow, but put enough arrows, right? But they're not going to count the arrows and mark you for that. Okay? So, 7.1.2 says calculate the magnitude of the electric field at point X. Now, remember, your equation for your electric field is E is equal to K times the charge divided by R squared. So let's substitute that in. That becomes 9 times 10 to the power of 9. Now, what is the charge? Here's the thing. I always remember it like this. M-U-N-P. Munip or munip. Okay, and then I'll go 3, 6, 9, 12. So I always remember munip, 3, 6, 9, 12. I am dealing with nanocoulombs. So this is over here, the N. So that becomes 4 times 10 to the power of negative 9 divided by my distance, which was 0.025 squared. You type this on your calculator and that you get that your electric field becomes 5,700 or 57,600 newtons per coulomb. Okay? Does that make sense? Okay, guys? You can give a thumbs up or a thumbs down if that doesn't make sense. Okay, I assume it makes sense, guys. All right, perfect. There we go. So, guys, please remember this little thing over here. Okay, guys, please. Otherwise, then you get a bit confused. Okay, so it's always munip 36912. Right? So M is for micrometers. This U is for M is for millimeters or milli units. U is for micro units. N is for nano units, and P is for pico units. All right. So guys, someone's saying, must direction be included? So let's read the question again. It says calculate the magnitude. Okay, that means we need to just know the size of it. We are not concerned about the direction. We just want to know the size of this thing. If there was a given charge, if there was a charge, can you just be a little bit more specific, Fadazi? I think that's Fadzai. I can't pronounce your name. I'm so sorry. If there was a charge given at X, would you use? So remember, X is just a point. All right. So we do not know the charge of X, right? We only know the charge of this thing. So X is some little point. It's not an actual charge. It's just a little point somewhere around this electric field. Okay. So X doesn't have a charge. Anyways, let's move on. Now, here is the juicy question. I think this was the only 6-mark question in the entire paper. All right. Not a definition. You'll see now. So what does it say? It says 2 identical neutral polystyrene balls, A and B, are suspended from a ceiling by an insulated, light, inextensible string, both of equal length, as shown below. So we first start off over here by 1. Okay. Ball B is given an initial negative charge. So that's supposed to be Q sub B, all right, of an unknown magnitude. So someone said, say if I wrote 5.76 times 10 to the power of yes, it is incorrect because remember, -8 means it's 0.0000 nanocoulombs. All right, so that would have been wrong. It should have been +8. I don't think that's 8, eh? Let's just see. It's 1, 2, 3, 4, right? It should be 10 to the power of 4, not 8. Anyways, So guys, we have given charge B some sort of a negative charge, okay? So we've made it a negative charge, right? The balls then attract each other, touch, and then repel each other. The balls come to rest with their centers about 10 centimeters apart, so that each string makes an angle with the vertical of 9 degrees. Okay, so it's this one. So this is part 2, right? We make B negative. A still remains neutral. It's still 0 coulombs. Then what happens? They attract each other. They exchange a charge. A new charge is formed. So therefore, Q new here. A new charge is formed over here. And as a result, this new charge pushes the two balls apart. So there's some force of repulsion over here. I'm going to put F REP. REP is for repulsion. Okay. And they come to rest at about 10 centimeters apart. So 7.2.1 is your definition question. That is the definition for Coulomb's law. 7.2.2 says calculate the magnitude of the initial charge of our ball B, the initial charge given to ball B if the mass of each ball was 0.012 kilogram. And that is for a juicy 6 marks. So I'm going to take you back to this scenario. Okay, remember the mass of both balls. Okay, I'm going to say M is 0.012 kilograms. So that's the mass of ball A is 0.012 kilograms. And the mass of ball B is also 0.012 kilograms. What do we want to know? We want to know this thing over here. What was the value of that negative charge that I gave to ball B? So what was that charge of ball B before it attracted the other ball and before it led to the situation at number 3 over here? So you guys are going to answer that one for me. I love giving you the difficult questions. All right. So guys, this is your answer, right? This is the proper one. This is going to see who's the cool kids and who's not. Okay. So you have 6 minutes to try and answer this question for me, guys. Don't be scared. All right. I'll give you a clue. Your force diagram will be your best friend for answering this question. Okay, guys? So you have 6 minutes to try and figure out this question. Your time starts now. And remember, post your answers in the chat. Okay, guys, so I'm seeing answers. I'm seeing answers that are fluctuating around negative 2.9 times 10 to the power of 7 to negative 2.88 times 10 to the power of 7. Negative 7, sorry. Guys, that is what the right answer is. All right, it's around that value. So, guys, you guys are doing very well. So, I expect all of you guys to get an 80% for this test or above. If you guys do not get 80 or above for your final, for paper one, I'll be very disappointed because you guys clearly know what your work is. You guys clearly know your work. So, well done, guys. So, let's get into the answers. Okay. So, let's see. All right. So, moved a bit too high. There we go. Let's look at ball B. All right. So this is ball B. Remember what I said? I said your best friend for this are your force diagrams. So let me just draw one. So this is a little force diagram for ball B. There, that's the tension on the rope. Ball B has some sort of a weight because they've told me this is the mass of ball B. And finally, it's there. What's that? That's the force of repulsion. That's pushing ball B away. All right. Now, what I'm going to do is I'm going to take this tension and I'm going to make it into its horizontal component and its vertical component. Okay. So I'm just going to get rid of that. Remember, in physics, we like things happening either vertically or horizontally. We do not like forces at angles. So what do? We break them down into their components. Okay. So what can I do now? Well, let's look at the net force in the x direction, all right? So I know that the net force in the x direction is equal to 0. Why is it equal to 0? Because they told me it came at rest. If your net force is equal to 0, that means that all the forces going one side is equal to all the forces going the other side. So that force of repulsion is equal to my tension in the x direction. What can I do now? Okay. I do not know what tension is in the x direction, but what do I know? Well, I'm going to take it to this diagram, right? So this is B, and that is the angle at which the tension is acting, all right? What is the value of this angle? Let's look over here. This side is 81 degrees, because remember this is 90. 90 minus 9 is 81. And remember, your ceiling is parallel to the horizontal, okay? Because you're focusing on the horizontal and your ceiling is parallel to your horizontal. So therefore, this angle theta is 81 degrees. So that's what I know. I'm just going to write it here. Theta is 81 degrees. Bam. What can I do now? Well, I know that tension is equal to, tension in the x direction is my tension force times the cos or the cosine of theta. And that is equal to my force of repulsion. But I'm still a bit stuck. I still do not know what tension is. But I can look at the vertical components, okay? The forces that are acting vertically. So I'm going to work over here and I'm going to say that the net force in the vertical direction or in my y direction is 0. So that means that my tension in the y direction is equal to my tension, to my weight of the object. Remember, tension in the y direction is T times the sine of theta, and that is equal to mg. So therefore, guys, I know that tension is simply the weight divided by the sine of theta, okay? Remember, your force diagram is your best friend when figuring this out, okay? Anyways, so that is what my value for tension is. So now I can substitute this, all right? I can substitute this value over here. So this becomes mg over the sine of theta is equal, multiplied by cos of theta is equal to my force of repulsion. Okay, because I first want to figure out what is that force that's busy pushing sphere B away. So I substitute this becomes 0.012 times 9,8 divided by the sine of 81 degrees multiplied by the cosine of 81 degrees. And what you do, guys, you type that on your calculator and you get that the force of repulsion is equal to 0.018626 newtons. Okay, so that is the force at which these balls are pushing each other away. Okay, so what can I do now? I know that there is a force of repulsion. There is an electrostatic force of repulsion. What can I do now? I'll work on the next page. If I know the force of repulsion, I can actually figure out what is the new charge on sphere A and sphere B. So I'm going to work on this slide. I'm going to say that the force of repulsion is equal to K times the charge of A, or the new charge of A, times the new charge of B divided by R squared. Now, here's the thing. Both of these spheres have the same charge. So what does that mean? It means that the charge of sphere A, or the new charge of sphere A, is equal to the new charge of sphere B. So this is equal to K times Q squared divided by R squared. So now I just have to figure out, okay, what is this new charge? So what I do is I just substitute. So this becomes the force of repulsion was 0.0186626, and that is equal to K, which is 9, times 10 to the power of 9 times Q squared divided by R. Now remember, the distance was in centimeters. It has to first be in meters. So I first have to convert it into meters, which is 0.1 meters squared. You do basic algebra and you get that Q squared is equal to 2.06955 times 10 to the power of negative 14. So therefore Q, all right, or the new charge of B and C is equal to 1.4385 times 10 to the power of negative 7 coulombs. Bam. Are we all up to date with this? Are we all following? So let me just take you to the picture. Let me just take out my highlighter. I first had to figure out, okay, what was this force of repulsion? I did that using, Newton's second laws. Then once I found that, I said, okay, if I know the force of repulsion, I can figure out the new charge between sphere A and sphere B. And remember, both of them have the same charge. Okay, what can I do now? So, I'm just going to change my color. Oops. Just give me a second. Oops. I'm going to change. I'm a bit bored of dark blue. There we go. And I'm going to make a little box here. Choops. Choops. So, I know the new charge of sphere B. Now, I want you guys to remember, how do we calculate the new charge on our spheres after they have touched? Because remember, they've touched and they've pushed each other away. So how do I figure out the new charge? Remember, Q new is equal to Q1, the charge of sphere A plus the charge of sphere B divided by 2. Okay? Now, here's the thing. When you figure out your Q new, your new charge, number one, you have to take their charges into consideration. Meaning, if it's a positive charge, then you have to say plus QB. If it's a negative charge, you have to say minus QB. That's what we use to calculate the new charge. Okay, so that means that Q new is equal to, well, what was the original charge of sphere A, right? The original charge of sphere A was 0. So that is 0. What is the original charge of sphere B? Remember, you've made it a negative. So that becomes minus QB over 2. So therefore, QB is equal to negative 2 multiplied by our new charge. All right? I hope we understand that. Now all we do is the only thing we have to do, we have to substitute. That becomes negative 2 times 1.4385 2.85 times 10 to the power of -7. And therefore, you type this in on your calculator and you get that the charge, or this original negative charge that I gave sphere B, is equal to negative 2.88 times 10 to the power of -7 coulombs. And there is your final answer. Now, I see some people got 2.9. Guys, it would have, this answer, final answer, would have depended on how you rounded off during your calculation. And usually for these types of questions, they have a certain range which your answer can fall. So it can be negative 2.88, or it can be or negative 2.91. They would have given you a certain range. As long as your calculations were correct, you should have gotten that. So well done to those people who have gotten it. For those of you who haven't, I hope you understand how I got it. I kind of had to work backwards, all right? So someone said they were still writing something. So here is the previous page. But guys, for the rest of us, do we understand how we got to this answer? Please, guys, take your opportunity to ask the questions. Remember, if you do not know, you do not know. It's not a big deal, all right? Ask, don't be shy to ask, all right? Okay, so if you understand, you can give a thumbs up. If you don't understand, okay. So Daniela would like me to repeat. So, firstly, when answering these questions, you first need to ask yourself, what is happening? So I'm going to do this again. Erase all ink. Yeah. So, what happened? All right, take black. This sphere A had an original charge of 0 coulombs. Okay. Now, what did I do? I gave sphere B a original negative charge. How do I know that? They've told me in the scenario. Okay. I think we all can agree with that. I have given sphere B a negative charge. That's what they've told me. Now, what happens? Because there's a difference in charge, they attract each other. All right. And when they attract each other, they exchange electrons and negative charges, and they form a new charge. All right. And that new charge is the same between sphere A and sphere B. So both sphere A and B have this new charge, Q new, Q new. All right. And because they both have the same charge, they end up pushing each other away like that. All right. That's what happens. And guys, this is all given to us. All right. So they push each other away, and there's this force of repulsion. Okay. And I'm going to put FREP. That stands for repulsion. So do we all understand this part? Okay. I gave B a negative charge. It attracted A. They exchanged charge. Both of them got the same new charge. They pushed each other away. And then they came to rest. They kept like this. They didn't move. They were staying like this. Now, this is a bit much, so I'm going to take out my highlighter. What I did was step 1. Always when you're answering these questions, your best friend is your force diagram. So that's what I did over here, guys. I drew my force diagram. And I realized that the 4 forces acting on it was my tension in the X and the Y direction, my repulsion force on sphere B, as well, as well as my weight. Okay? So, how do we know that the initial charge of A was 0? 2 identical neutral polystyrene balls. Okay, then later they say ball B is given an initial negative charge. So that's how I knew. Anyways, so I first figured out, okay, what is the tension? Oh, sorry, what is the forces acting on my ball? Then I realized I can figure out what the force of repulsion is. All right, so I said that F net is equal to 0. So therefore the force of repulsion is the same as my tension in the X direction. Why? Because they told me that these things were at rest. If your net force is equal to 0, or if you're at rest, it means your net force is 0, which means that all the forces going one side is the same as all the forces going the other side. All right? You could have used 9 as your angle. You could have used it. You could have used it, then it would have become tan of theta. But I just like this method a bit better. Anyways, so now I know that tension in the X direction is T times cos of theta. all right? And that is equal to my repulsion force. But I still had to figure out, okay, what is tension? So then I had to look at my force diagram and I go, oh, I can look at the forces in the vertical direction. My F net in the y direction, again, is still equal to 0. How do I know? Because they tell me the balls came to rest at that position, okay? So therefore, it means that all the forces going up was the same as all the forces going down. So that means that tension, or the vertical component of tension, was equal to mg. So therefore, I got the value of tension, which was this value over here. Okay? Then what I did was I took this and I substituted that into my equation over here. So this was the original value. I substituted that and I simply filled in the values and I got that. The force of repulsion was this over here. And I didn't even round off. You only round off at the very end. I hope we understand that. If you do not, you might have to play that recording once or twice again. Okay. And maybe even try and practice the question on your own. Anyways, then I said, okay, I know the force of repulsion between the two spheres. I also know that these two charges are the same. What can I do now? What I can do, I can figure out what is the value of this new charge because I also know the distance. So that's what I did for my second part. I figured out, okay, what is this new charge on each sphere? And I got this 1.4 times 10 to the power of -7 coulombs. Now I say, okay, that is the value for my new charge on each sphere. All right. How do I figure out the original charge of sphere B? I use this equation. Now, this is not given to you on your formula sheet as far as I remember. So therefore, you actually have to remember this. Okay. So, guys, this is the value of my new charge. The new charge is equal to the original charge of sphere A plus the original charge of sphere B divided by 2. All right? Remember, sphere A had 0 charge because it's neutral. Sphere B got given a negative charge. That's why we say it's negative over here. Okay? I made the original charge of sphere B the subject of the formula. So the original charge of sphere B just became -2 times the new charge. Okay? And then I typed this into my calculator. And I got this value over here. All right? I hope that makes sense. Okay? If it doesn't, you just might have to watch the video again, replay it a few times, and maybe even try and answer it yourself. Okay, guys? But I'm glad hopefully you guys could understand the way I explained it. Okay. So moving on. Get my pen out. Pen. There we go. No, that's not a pen. That's a highlighter. There we go. Perfect. So moving on. We have now finished question 7. We finished probably the most difficult question in this paper. Now we can get on to circuits. Ooh, more reading. So it says, or it states over here in the scenario, a battery of an EMF of 12 volts and an internal resistance of 0.2 ohms is connected to 3 resistors, a high resistance voltmeter. Okay, so basically, guys, they are explaining the circuit diagram over here. Okay, the EMF is 12 volts, your internal resistance is 0.2 ohms, and each resistor has a different resistance. Okay, that's basically what this whole scenario explains. Now it says here, the resistance of resistor Y is twice the resistance of resistor X. So that therefore means that resistance Y is twice Rx. Okay, that's what it is. And that's quite an important bit of information. When both switches are closed, okay, the reading on the ammeter is 5.5 amps. So here, it's 5.5 amps. Okay, so that's what's been given to me. Okay, 8.1 says, give a reason why there is no current flowing through resistor Z. So remember, this switch is closed, so there's no current flowing through resistor Z. Why is that? You guys can answer that for me quickly in the chat. I'll give you 30 seconds. So can someone please explain why resistor Z gets absolutely no current. Okay, you guys can answer that in the chat. Okay, so I think it's Mikola or Michaela said the path of least resistance. So you are correct, but remember, you need to actually answer a little bit more carefully, right? I mean, like answer in proper sentences, no, like, you know, otherwise, if you just put that like a one-word answer, your examiner might not even mark it correctly. So guys, try and write your explanations in full sentences. Perfect, guys. So you guys will all get the answer. Remember, my current is going to take the path of least resistance. This path in which S1 is situated has basically zero resistance. So I've short-circuited over here, which means that there is absolutely no current which goes through resistor Z. So it just skips this path and goes here. So I can completely ignore resistor Z. So I just have two resistors in parallel in my circuit for this situation. So I'll just say you have created a short circuit. Okay, there we go. Well done, guys, for answering. Thank you for answering. Now it states, calculate the resistance of resistor R in the Y. So what can I do now? What can I do? Well, based on all this information that they've given me, all right, I can use this equation. I'm going to say that the EMF is equal to my current plus big R and little r. But here's the thing. Big R is essentially your external resistance. Now remember, I only have two resistors in parallel. I'm going to ignore R in the Y direction, RZ, Y, because they have told me there is no current going through it. Over here, 8.1, give a reason why there's no current going through resistor Z. So I can ignore it. So I have a simple circuit with two resistors in parallel. So that simply means that the total external resistance is equal to the parallel resistance, or my total parallel resistance. So what can I do now? Well, what I can do is I can actually figure out what is the value for my total external resistance. So all I need to do is I need to substitute. So it comes 12 is equal to my total current, which was 5.5, times my total parallel resistance, which is the same as my external resistance, plus 0.2. So you get that R parallel plus 0.2 is equal to 12 divided by 5.5. That's 109 over 55. Okay? So therefore, the total resistance in parallel is 109 over 55 minus 0.2. Oh, sorry. Oops. That is 24 over 11. So therefore, 24 over 11 minus 0.2, that becomes 109 over 55 ohms. Okay. So that's the total parallel resistance. Remember, my total external resistance is the same as my total parallel resistance because I have two resistors in parallel. What can I do now? Well, now I can figure out what the value of resistor Y is, okay? So I know that 1 over R parallel is equal to 1 over R in the X direct, or sorry, Rx, plus 1 over Ry, okay? Now remember, we have been told that Ry is twice Rx. So this becomes 1 over Rx plus 1 over 2 Rx, okay? That is 1 over R parallel. Now, I know some of you guys get taught the resistance in parallel is product over sum. Guys, that only works if you have two resistors in parallel. But if you have a situation where you might have three resistors in parallel, then that equation doesn't work. So I prefer this one where you do it the long way. Okay? So if you solve this, you get that 1 over R parallel is equal to this becomes 3rx divided by 2rx squared. Okay, you multiply your denominators and then you go, it's basic algebra. Okay, so therefore, r parallel is equal to 2 over 3 rx squared divided by rx. Your rx at the bottom cancels out with one of the rx's on the top, and we're left with something that looks like this. I'm just going to rub it out and redo it. Rx. So what I can do now I can figure out what is the value for my resistor X. So R parallel was 1 over 9 over 55, and that is equal to 2 over 3 Rx. So therefore, the value of my resistor X is equal to, type this on your calculator, and you get that this is 2.9727 ohms. Okay? Now remember, the value of resistor Y was 2 times the value of resistor X. So therefore, that becomes 2 times your answer. So therefore, the value of my resistor Y becomes 5.95 ohms. And there we go. Okay, guys, do we understand that? So you first had to calculate, let me just block this off here, there. So we first had to calculate what was the total external resistance. The total external resistance is the same as my parallel resistance because I have a short circuit. Then what I had to do is I first could figure out, okay, what is the value for resistor X? Once I figured out the value for resistor X, I got the value for resistor Y. How did I get 3 over 2? Okay, let me show you. I'm just going to work here. Okay, ignore the question. So I had 1 over Rx plus 1 over Ry. Now, we were told in the beginning that Ry was twice resistor X. So that becomes 2 times resistor X. When you add fractions, you multiply the denominators. So that becomes 2 times Rx times Rx. Okay? Now, what you do is you do this. This multiplied by that becomes 2Rx. Rx multiplied by 1 becomes plus Rx. So therefore, that becomes 3Rx over 2Rx squared. And that was 1 over R parallel. Remember, your final step is you flip everything. So therefore, R parallel was simply equal to 2 over 3 Rx squared divided by Rx. It'll just give you Rx. And there we go. Did that answer your question? Okay, perfect. I hope it did. Anyways, guys, that is how we got the value for resistor Y, and we also managed to figure out the value for resistor X. So someone also asked, please explain more about short circuits. How does one identify and how does... So guys, a short circuit is basically when you have a pathway that has no resistance, okay? Like what we saw over here. Here is a pathway that has no resistance. So that's when you generate a short circuit. And what a short circuit does is, depending on the situation, it increases the current because now the current is going to move through the path that has the least resistance. And as a result, when it moves through the path of least resistance, it's going to increase the current. That can do a lot of things. If you're dealing with internal voltage, it can increase the lost volt. Your lost volt is basically the heat that your battery gives off. If you make a short circuit, you increase the heat of your battery. Okay. Don't try this at home, but if you ever take a battery and connect 2 copper wires at the end of it, you have made a short circuit because there's no resistance. And if you fuel your battery after a very short amount of time, your battery is going to get very hot. Do not try it at home because your battery can explode. Anyways, so guys, this is 8.2. All right, hopefully you understand that. Okay, so you guys written it down. 8.3 says, calculate the power dissipated by resistor X. Okay. Guys, I'm going to let you answer this one. All right. So you guys have 3 minutes. Okay, we are a bit pressed for time, so I'm going to give you 3 minutes to try and answer this question. And your time starts now. Okay, guys, so I see some people said 39.97. Someone said 39.96. Someone said 40.003 watts. So, guys, your answer is in the right range. So, well done, guys. I just know we are all going to get 90% for paper one. I expect that. Okay. So, let's figure out how we can solve this answer. So, what's the equation for power? And what I want to do is I want to find the equation that kind of requires the least amount of work, okay, the least amount of effort from me. So I found this equation. I found that power is V squared over R. Okay, R is that for resistor X. So what can I do now? Well, here's the thing. I am still dealing with a parallel circuit because this resistor Z I got rid of. Okay, it doesn't exist. Now, can you see me? Okay, guys, apologies from that. Let me just start sharing my screen again. Yeah, this internet is being a bit of a, I have a word to describe how the internet is being, but I will not use it over here. Okay, it is not an appropriate word. Okay. All right, so just give me a second. Give me a second quickly. Hmm. Sorry guys, my Teams just froze, so it's just being stupid now. I'm just gonna exit and then enter again. Apologies for that. Okay, guys, I do apologize for that. Sorry, I am back. This Wi-Fi is being a pain in the. I will not say it. Anyways, so guys, let me just get up my pen quickly. So I know that power is simply V squared over R. All right, and we are dealing with resistor X. Okay, here we go. Sorry. Yeah. Now, what do I know? I know that in a parallel circuit, the voltage stays the same. okay, the current divides. Okay, so what does that mean? That means that the voltage going through this branch is the same as the voltage going through this branch. Now, what is the voltage being supplied here? Because I only have those two resistors that are in parallel, the voltage going through this branch is my external voltage. And the same can be said for this branch, okay? So what I need to do is, I also, by the way, know the value of resistor X. So what I need to do is, I need to figure out what is my external voltage, okay? So there's different ways you can do that. I'm going to do it like this. I'll say that firstly, my external voltage is the current times the total external resistance. Okay, because that's the voltage going through my entire circuit. So that becomes 5.5 times 109 over 55. And you type that on your calculator, and then you get that your external voltage is equal to 10.9 volts. So what does that mean? That means that in each branch, we are getting 10.9 volts of energy, okay? So now I can calculate the power. Power is simply the external voltage, 10.9 squared, divided by our resistance. And what was the resistor for resistor X? It was 2.9727. You type this on your calculator and you get that your power is 39.96 volts. Okay? Do we understand how we got that? All right? I first had to figure out, what I like to do is I first try and find which is the equation that requires the least amount of effort from me, because I don't want to waste ink on too much equations. Okay? I have a long test to write. So I do that. I find that my external voltage is 10.9 volts. Okay? Now that I know my external voltage, I can figure out the power going through that resistor, or the power that that resistor is dissipating. And that's my answer. Okay, I hope we understand that. So 8.4 says, when both switches are now opened, the reading on the ammeter is 1.3 amps. Okay, so both switches are open. So what does that mean? That firstly means there's no longer any current going through resistor X. And this current means that there's no current going through this branch. So I only have two resistors, and both of them are in series. Thank you for that. Power is in watts or joules per second. Okay, thank you for that. Thank you for pointing that out. Anyways, I have two resistors in series now. Why? Because both switches have been opened. Now they ask, calculate the reading on our voltmeter over here. And they also said the new current is 1.3 amps. So I is equal to 1.3 amps. Okay. So now we need to figure out, okay, what is the value for my new current? Oh, sorry. What is the new voltage going through V? Now I'm dealing with, firstly, a series circuit. What do I know about series? The current in each branch is the same. So current remains the same, but the voltage divides proportionally. Okay, what does that mean? The current going through each resistor is going to be the same no matter what, but the voltage divides proportionally, meaning that the resistor with the highest resistance is going to get the most voltage. The resistor with the lowest resistance gets the least amount of voltage. That's what it means. And if you want to figure out the voltage going through that specific resistor, you have to use the resistance of that specific resistor. So therefore, the reading on my voltmeter will be the current times the resistance of resistor Y. Okay? So that becomes 1.3 times 5.95. Okay? And therefore, the reading becomes 8.925 volts. And there we go. Okay? That's pretty easy. Alrighty. Now let's get to 8.5. Almost done, guys. We just have 2 more questions. Hang in there. We are almost done. Okay. What does it say? It says switch S remains open, but switch S1 remains open while switch S2 is now closed. Okay. So we still have no more current going through here. However, this one is now closed. So now we have a parallel branch and we have a series, a resistor in series. So 2 resistors in parallel, 1 resistor in series. And we need to figure out what is the reading on our ammeter. So what is the new current? So how do we figure that out? Okay, guys, so how did we figure that out? So what I'm going to do is I'm going to do this. I think, yeah. So what I'm going to do is I'm going to do this, okay? I know that the EMF is equal to I times big R plus little r, right? What I'm going to go look at everything beforehand, okay? In this situation, right? Because I actually first want to find out what is the value of resistor Z. If I figure out what the value of resistor Z is, it can help me a lot. So step 1, let's find the value of resistor Z. Okay, so originally we knew when both these switches were open, right? This was the first thing. When both of these switches were open, we knew that the current was 1.3 amps. All right. We don't know what the total external resistance is. However, the internal resistance always remains the same, as well as your EMF. Okay, so guys, remember, I'm now trying to figure out what is the value of resistor, Z. Okay, so what you do is you solve for this and you get that my total external resistance for the situation when both switches were open was equal to 9.03 ohms. Bam. Okay. So I have that. What can I do now? Well, I know that the total external resistance, remember we are still with the situation where both switches are open, is equal to Ry plus Rx. Okay. Oh, sorry. I'm starting to now lose a bit of focus here. I do apologize. So it's equal to the total external resistance was Ry plus Rz. Now, guys, we already calculated the value for Rz, okay? So therefore, Rz is simply the total external resistance minus Ry. And we get that Rz is equal to 3.08 ohms. This is Rz. Bam. So what do I know now? Okay. I first figured out, okay, this is the resistance of Rz. Now, remember for my next situation, I close switch S2, so it looks something like this, okay? So now I have a parallel branch and I have a resistor in series. So what can I do now? I'm going to change the color a bit. Now I can figure out the new current, okay? So this was the original current that was for the previous scenario. Now I'm going to figure out the new current. Again, I'm going to use this equation. EMF is I times the big R plus little r, okay? And what I'm going to do is, I know that my external resistance, remember big R is your external resistance, is simply the resistance of Rz plus my total resistance for this whole parallel branch, okay? So that becomes 3.08, because we've calculated that already, plus, now what is the resistance for that entire parallel branch? Remember, we figured it out in the previous scenario, right? We figured it out over here, okay? That it becomes 109 over 55, And therefore, if you type that on your calculator, you get 5.0618 ohms. Okay, so that's my total external resistance. Now I can finally calculate my current. So remember, my EMF is still 12 volts. It's equal to this new current, right? When switch S2 is closed and when switch S2 is closed and S1 is open, plus my resistance. And what's my resistance? It's 5.0618 plus my internal resistance, which is 0.2. And what you guys do is you type this all on your calculator and you get that I is equal to 2.28 amps. Bam. Again, let me now show you what I've done. Step one, I first had to figure out, okay, what is the value for resistor Z? I used the previous situation where switch S1 and S2 were both opened, okay? Which meant that I was dealing with RY and RZ that were in series. I figured out that the total external resistance was 9.03 ohms, okay, over here. And then I used that information to calculate the value of resistor Z. Then what I did was I used now the situation where S2 was closed and S1 remained open, okay? Again, I used this equation over here, and I realized that the total external resistance is basically the value of RZ plus the value of R parallel. Okay, now remember, we calculated what was the total resistance for that parallel branch. I just had to add it to RZ, and I get that the total external resistance is 5.0618, okay, ohms. I then use that to solve for current, and this is the value for my current. Do we understand that? Okay. You guys can say yes or no. You can post a thumbs up or a thumbs down if you don't understand. But guys, do we get this? Perfect. May you please check your answer in 8.4. Okay, so what are you not sure of? Luyanda. So you said I got 7.722. Remember, the resistor for resistance Y was 5.95 ohms. The current was 1.3 amps because they've told us that. So therefore, the voltage going through resistor Y's branch is equal to 8.925 volts. What are you unsure of with your answer? You can just type it in the chat and I can help you, Nana. Okay. So guys, do we understand how I got to my answer? I see most of us send a thumbs up. Perfect. Almost done. Question 9. So, Luyanda, just state where you think you went wrong and I can assist you, Nana. So question 9, this is your motors and generators section. Almost done, guys. Almost, just wait to be keep up. So answer must be 7.4. Let's just see quickly. I want to check on my calculator. So it's 1.3 times 5.95. And you guys are correct. I think I might have written this incorrectly. This is 7.735 volts. Good eye, guys. Well done, well done. I think I just miscalculated it or typed it wrong on my calculator. But good spot, eh? Thank you for that. It's 7.74. Okay. Yeah. Luckily for the other questions, I didn't actually have to use that voltage, so it didn't affect my answer. So this, guys, this answer is correct because I didn't even use that voltage. But good eye. Thank you for spotting that out. Okay. Anyways, moving on. So guys, this is our motors and generators question. So it says the simplified diagram below represents an AC generator and it's moving clockwise. 9.1 asks, what is the direction of the current in our electrical circuit? So we are focusing over here. Okay. So is it from Y to X or is it from X to Y? Right, remember, we are moving clockwise. So guys, you can actually answer that question for me. Is it Y to X or X to Y? I'll give you 1 minute because it's for 2 marks, but I'll give you 1 minute to answer that, starting now. Okay, so I'm seeing a lot of divide here in the answer. Some people are saying X to Y, some people are saying Y to X. Let's figure it out, guys. Almost done, I promise you. So remember, the battery always goes, the magnet always goes from north to south. So it's doing something like that. And remember, because we are dealing with a generator, because they've told us that, we use our right-hand rule, generator. That's how I remember it. Okay, so number one, I like to look at the magnetic field first. I'll go, okay, where is that magnetic field going? It is going from left to right. So I point my finger there. Okay, now remember, the current going through here is the same as the current going through. Let me just take out a different highlighter. It's the same as the current going through here, okay? Because you know they're connected in the circuit. So whatever happening here is the same as what's ever happening over here, okay? So number one, I know that my battery, or sorry, the magnet is going from north to south, so from left to right. Number two, what is happening to this yellow section of my coil? Is it moving down or is it moving up? It is being moved down. So my force is going down like that. Okay, so it looks something like this. And finally, what do? I stick out my middle finger. Sounds very, anyways, I stick out my middle finger and I see that, oh, it's going from Y to X. So the answer here, guys, let's take out a different pen. Oh, it is from Y to X. Again, start with your finger. The magnetic field always goes from north to south, so it's going from left to right. What's happening to that side of the coil? It is being moved down. And then finally, you shoot out your finger. Oh, it's going from Y to X. There we go. State the energy conversion that takes place in a generator. It always starts from mechanical energy, energy, and it gets turned into electrical energy. Okay? Pretty simple. Now it says the maximum voltage produced by the generator is, what is it? It is 125 volts. Okay. Well, you do not learn it in school yet. Hi. Okay. Remember, for a generator, you use your right hand. For a motor, you use your left hand. Generator right hand rule. And remember, I always go FBI. FBI, FBI. F is your force, B is your magnetic field, I is your current. F is the symbol for force, B is the symbol for your magnetic field strength, and I is the symbol for current. Okay, so FBI. Always remember that. When you deal with this, you always go, okay, number one, where is my current going? It's going from north to south. So wherever north and south is, we do that. Okay, if it's going from right to left, we point our finger here. Then your thumb tells you where the force is. If this side is going down, then your force is going down. If this side is going up, your force is going up. And then finally, you stick out your middle finger, and then that tells you where the current is going. So I always start off my force, I start off with where is my magnetic field going? Then I start off, is it going up? Is it going down? And then I shoot out my finger for the direction of the current. Okay. Anyways, guys, it says that the maximum voltage produced is 125 volts. Define this term, the root mean square of voltage. There is your definition. Okay. Now it says calculate the root mean square voltage, the VRMS of the generator. So we know that VRMS is equal to your maximum divided by the square root of 2. Okay. That becomes 125 over square root 2, and therefore my VRMS is simply equal to 88.39 volts. Done. Bam. There's your answer, an easy 3 marks. Okay. Then we go, yeah. It says that the total external resistance of the circuit is 42.4 ohms. Calculate the maximum current induced. Okay, remember, IRMS is equal to Imax over square root 2. So what I need to first do is I need to go, okay, what is the value for my IRMS? Now, we remember from circuits that I is equal to V over R. Okay, that's for the normal circuit. Okay, so if it's a generator, just want to show you the picture. You see there are two different rings. Okay, those are called slip rings. Okay, so if you see two separate rings, that immediately tells you it is a AC device. All right. Secondly, you can see that it is connected to a resistor, not a battery. If it's connected to a battery, then it's a motor. If it's connected to a resistor, it is a generator. Okay, hopefully that assisted you. Now, we know that current for a normal circuit is I is equal to V over R. However, when dealing with an AC circuit, it changes slightly. I know that the IRMS is equal to the VRMS divided by R. So for AC circuits, your I changes to IRMS. Okay. Now I know what the VRMS is. I've calculated that in the previous scenario. So therefore, IRMS is simply equal to my VRMS, which is 88.39 divided by 42.4. And my IRMS is equal to 2.08. Now I know my IRMS, I can figure out my maximum current. So therefore, Imax is equal to the square root of 2 times my IRMS, which is equal to the square root of 2 times 2.08. Therefore, my maximum current that this thing generates is equal to 2.95 amps. And Bob's your uncle, okay? Hopefully you guys understand that. Okay? Pretty simple. This is usually a quick, easy section. Now, the final question for this is, the generator induced a current at a frequency of 20 hertz. The coil started rotating from the initial position as shown in the diagram above. Sketch the graph of induced current versus time for 2 complete rotations. So 2 complete rotation of the coil. What we need to indicate is number 1, the time for 2 rotations, and number 2, the maximum current by the generator. So number 1, what do I know? Number 1, this is AC. That's the first thing I know. Number 2, what is the time for 1 rotation? Remember, time for 1 rotation, the answer point for 1.5 was 2.95 amps. Remember, time is equal to 1 over the frequency. Now, what's the frequency? It is 20 hertz. So therefore, 1 over 20 is equal to 0.05 seconds. So that's how long it takes for this thing to make 1 full rotation. We want to know how long does it take for this thing to make 2 complete rotations. Number 3, I know that if this is our 2 magnets, north and south, our coil started at this position, right? When your coil is completely flat, you have the maximum amount of current or voltage. When your coil is vertical, it is 0. Flat, it's the maximum value. Vertical, it is 0. Okay, so let's draw our graph. The y-axis, we know it's our induced current, our current in terms of A, and then this is time. Now we know, because we saw that 2 split rings, we know that this is alternating current. So this is going to make something like this. But we want it for 2 rotations. So it's 1 2. Okay, so we've drawn our graph. Now, what were the instructions? We want to know, it says, indicate the time taken for 2 rotations. So we know that for 1 rotation, it was 0.05 seconds. So how long would it take to make another full rotation? It would take another 0.05 seconds, which means that the time for 2 full rotations is 0.1 seconds. I hope that makes sense. Now we also want to indicate the maximum current. So the maximum current was 2.95 amps. That's what we calculated. But because this is alternating current, we have a maximum and we also have a maximum in the opposite direction. Okay, there we go. And this is a negative. So it fluctuates between 2.95 volts in the positive and in the negative direction. Okay, you are absolutely correct. So let me just do it again. But you are right. We started at the maximum. So let's just do it again. So we started here and we do something like that. Oops, like that. And we go like that. So it looks like a cos graph, okay? Because we started flat, so we started at the maximum value. Thank you for pointing that out, okay? So it looks a little bit like a cos graph, okay? Remember, the time is still the same. For 1 full rotation, it took 0.05 seconds. For another full rotation, it took 0.1 seconds. Thank you guys for being a little bit awake and for spotting that out. I really appreciate it. Anyways, do we understand this graph? Okay. For those of you who haven't finished motors and generators yet, hopefully your teacher explains it to you before your exams start. But there we go. Okay. Quite simple. Question 10, our last question. Okay. Then we are almost finished. All right. Question 10 says, number 1, define the photoelectric effect. I've already defined it for you guys. We're not going to skip. Question 10.2 says, light of a wavelength 4.7 times 10 to the power of negative 7 meters is shone onto the surface of a piece of cesium metal. If the threshold frequency of cesium metal is 4.37 times 10 to the power 14, calculate the maximum speed of an electron ejected from the metal surface. Okay, guys, my throat is a bit sore, so you can answer this question and post the answer in the chat for me. Okay, so guys, answer the question and you can post it in the chat. Okay, you have 4 minutes to do that. Okay, guys, so I see some good answers here. Most people got around 541,292.7.69 meters per second. Okay, so let's see how we get to the answer. Well done, guys. It seems like it's the correct answer. Let's figure it out. Okay, I'm going to change color to red. So what do I know for the photoelectric effect? I know that the energy of my photon is the work function plus the maximum kinetic energy, okay? That's a formula given to us. If I expand this, this becomes HF is equal to HFO, which is my threshold frequency, plus 1 over 2m times my maximum velocity squared. And I want to know what is the value of this. Now, here's the thing. They gave me the wavelength of light, right? So we know that lambda is equal to the velocity of light, which is c, divided by the frequency. And therefore, the frequency is equal to the speed of light divided by lambda. Okay? So this becomes h times c over lambda is equal to h times FO plus 1 over 2 mv squared max. Okay? That's what I know. Okay, I just manipulated my equation to accommodate the wavelength of my light. So now I can substitute it. And with photoelectric effect, the numbers that you have to sub in is very, very small numbers, okay? And then the speed of light is quite big. So I firstly know that h times c over lambda is equal to h times FO, where h is Planck's constant, plus 1 over 2m times velocity squared, or your maximum velocity squared. Now we substitute it in. This becomes 6.63 times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8 over 4.7 times 10 to the power of negative 7 is equal to Planck's constant, which is 6.63 times 10 to the power of negative 34 times the threshold frequency, which is 4.37 times 10 to the power of 14 plus 1 over 2. Now, what is m? Remember, m is the mass of our emitted electron. The mass of your electron is given to you. It's 9.11 times 10 to the power of negative 31 times v squared max. Okay? To simplify this, you type this all on your calculator and you get that this is 1. This side is 1.3346 times 10 to the power of negative 19. That's a 9 is equal to 1 over 2. Right? You just solve by using your calculator. 1 over 2 times 9.11 times 10 to the power of negative 31 times v squared max. Okay, guys? So I just skipped 1 or 2 steps. I just solved for this. And therefore, you get v squared max on its own. So v squared max is equal to about 2.93 times 10 to the power of 11. So therefore, the velocity or the maximum velocity is simply equal to 541,291.7 meters per second. And there we go. So guys, for those of you who got the answer, well done. You guys are correct. Okay, we are almost done with this lesson. We just have 3 little questions left. Okay? So, last one, right? So it states over here, and simple electroscope consists of a zinc disc, a metal stem, okay, a metal stem and a thin length of gold foil, as shown in diagram 1 below. Okay, sorry. When the electroscope is neutral, the foil hangs vertically, as shown in the diagram 1 below. When the electroscope is negatively charged, the foil is repelled from the stem, as shown in diagram 2. Okay, so these are your things that they show, okay? When ultraviolet is shone onto the disc, the charged zinc electroscope, all right, so when it's shone onto the disc of the charged zinc electroscope, the foil collapses, so it hangs vertically. How does the frequency of the ultraviolet light compare to the threshold frequency? Guys, you can state this in the chat. Remember, I am shining ultraviolet light and it's causing something to be emitted. All right, it's causing these electrons to be emitted. That makes this whole thing neutral and that causes it to collapse. So how does the frequency of ultraviolet light compare to that of my threshold frequency? It is greater than. Remember, this the emitting of electrons only occurs if the frequency of your source is greater than the threshold frequency, okay? The frequency of your light source. Well done. So, number 2 says, explain why the electroscope foil collapses. So why did it collapse? You guys can explain that for me. Second last question, why did it collapse? You guys can post it in the chat. You have 1 minute. I already explained it in the previous slide. Okay, so guys, explain for me why they were basically explain why there were electrons, or why did the electroscope collapse? Okay, minute. Okay, so guys, someone said, Sarah said, more electrons are emitted due to the higher frequency of UV light. This leaves the electroscope positively charged, thus attracting the negative foil. Okay, so guys, remember that answer is pretty much correct. So here's the thing. We know that the frequency of our source is greater than the threshold frequency. So therefore, electrons would be emitted. Okay? When electrons are emitted, the electroscope becomes neutral. Not positively charged, it becomes neutral. It loses that negative charge and becomes neutral. So therefore, it collapses. Okay, so well done, guys, on answering that. Very, very good answer. Okay, finally, green light is now shone on another negatively charged zinc electroscope. The foil does not collapse. So number one, I know that the frequency of my green light, I'm going to say G for green, is less than the threshold frequency of my zinc. Why do I know that? Well, it's because that foil did not collapse. It only collapses if there is electrons emitted. And clearly in this case, there was no electrons emitted. 10.3.3 asks, will the foil collapse if the intensity of green light is increased? Yes or no, and give a reason for your answer. So guys, try and answer that question for me again. What is going to happen if you increase the intensity? You guys can quickly state it. You can just say yes or no. Okay. I see an answer for yes. Interesting. Okay. We'll see if it's correct. Oh. Okay. So come, guys, one more question. Try and answer that last question. I see no, but guys, you must explain why. You can't just say no. I want an explanation why. There we go. I think it's Bonani. There we go. That is the best answer I was looking for. No. Remember, intensity is just the number of photons. Okay? That is very important, guys. Now, we originally were told that this foil does not collapse. So therefore, no electrons were emitted. So what's going to happen? If I increase the intensity, I'm just increasing the number of photons striking the surface. But I have done nothing to the energy of my photon, nothing to the wavelength, nothing to the... Oh, I'm so sorry about that, Michaela. I hope everything was all right. Oh, yeah. Sorry about that. Anyways, when you increase the intensity, it does nothing to the photon. It does nothing to the energy of your photon. It does nothing to the frequency. It does nothing to the wavelength. It only increases the number of photons. So I knew that originally this green light had not enough. My English is not Englishing. This green light did not have enough energy to emit the electrons, okay? Because they've told me that foil did not collapse. So if I increase the number of photons striking the surface, I'm going to do nothing to my emitted electrons. Why? Because in the first place, sorry guys, it's been a long day, as you can see. Remember, if you increase the number of photons striking the surface, it's not going to do much because the photons do not have enough energy to emit the electron. So I can chuck 1 trillion photons onto that surface. No electrons going to be emitted. So therefore, the answer is no. And you guys have all provided reasons. Okay. So guys, that is the end of our spring schools. I just want to say again, thank you so much for taking time out of your day. We really hope this lesson was able to provide a little bit of more insight into answering questions for paper 1. And looking at the answers that you guys have given me, I know all of us here are going to get 80% for physics for paper 1. Okay, I expect 80% for all of you. Okay. Thank you so much, guys. We are going to make the recordings available later tonight or maybe even tomorrow morning. But yeah, a big thank you. I'll be seeing you later in the week for maths paper 1. Okay. So hopefully we can be ready for paper 1. But guys, thank you so much. Good luck for your exams. Right. Tomorrow, guys, we'll be doing paper 2 chemistry where you'll be seeing my colleague Umar. Okay. So thank you so much, guys. Enjoy the rest of the afternoon and enjoy your school holidays. Okay. Bye-bye, guys, and study hard.